I'm very glad to really see CITA since CITA has very nice relation with Cambridge University where I was studying. So I see many of my friends, James and Richard, they are all my classmates before. So today I'm discussing the CMB, testing the CMB anisotropy for you, and some of these things I have been doing with George Astasio in Cambridge. And if you have any questions, then we can just easily discuss. It's a very informal lecture. Okay, so I want to separate this problem of testing CMB anisotropy into three different problems. The first one is to test the CMB angular correlation function, which is very often discussed in the recent literature. How to use angular correlation function to test the CMB anisotropy. And the second is that we can also test in the direction-dependent power spectrum directly. And some people have done this work with WMAP, and here I'm showing we do some forecast for fun as well. And the third one is probably a little bit interest for the theories is to testing different model of the early universe and also forecasting the detectability of this model of the early universe from the future CMB experiments from CMB4, etc. And we may focus on the detection from the B-mode polarization. Okay, so for the first part, for WMAP, people have been discussing very openly about the CMB angular correlation functions. So for those of you who are not really working in this field, I just quickly catch up the basic equations in these angular correlation function problems. So this question actually links to the problem of asking whether the universe is expressive isotropic. So does the universe really lack of large angular correlation? So these two things link together. If you have a CMB map, in which map you have a temperature fluctuation as a function of the angle on the map, so delta T as a function of the theta and psi angle coming through the spherical two-dimensional map, then this map could be decomposed as the ALMs and by using this spherical harmonic functions YLMs. So these ALMs are the coefficients. The angular correlation function C of theta is defined as the average of the product of the two fluctuations separated by angle of theta and average over the full sky. So if you substitute the delta T in this equation here, C of theta will be equal to this. Angular average goes to ALMs. So and ALMs if the temperature fluctuation is completely isotropic, then ALMs by doing average, this will link to the power spectrum, angular power spectrum, CLs. So C of theta eventually becomes a Reynolds transformation of these CLs. This sigma summation runs from the lowest multiple quadruple to some cutoff, which is I shown here as Lmax. And in reality, sum to the Lmax equal to 15 is enough because this C of theta is most sensitive to the lowest multiple. So till Lmax in summation is probably enough to get the C of theta function. The open discharge statistic, which is so-called S1 half, is defined in this form. S1 half, one half comes from the upper limit of this integral C of theta squared. So it's basically if cosine theta runs from -1 to 1/2, then actually theta is integrated from 60 degrees to 180 degrees. So this S1 half, by its definition, basically is measure the strength of the correlation function C of theta on the angle of 60 degrees and 180 degrees. So it's basically measure the strength of the C of theta above 60 degrees. So then later we will see why people even such a statistic. And also later we will see whether it's a good statistic or not. The argument of lack of large angular correlation function comes from here, Kopi et al. 2009. This is the angular correlation function, C of theta, as a function of theta. So if you they use a WMAP full sky LLC map, and they measure the full sky LLC map the angular correction function by just a simple 2-point average by taking angle theta from these equations, basically. By doing this average, they find AC of theta like this black real line here. And in the original map, you can probably see some residual contamination here, like here, here. Therefore, one can cut this out by applying a mask on this ILC map. This is a KQ75 mask, where basically the red region, the unmasked region, high latitude region is basically around 70% of the full sky area. So after you apply this mask onto this map, therefore you cut off the region on the graphic plane and compute this angular correction function, C of theta, from the previous equation that we showed doing the angular average of the the product of two fluctuation points. And people find the black dash line here, like this. I will see black dash line here, with this line here. And they argue that you see it's pretty flat above 63. This is not enough to quantify the significance. What they do is that they do a simulation of the isotropic universe. This is in the real universe S1 half number, which if there's no mask, you have 8,000 flat basically. You basically quantify the C of theta doing that equal, doing the integral of C of theta squared. They get 8,000 basically for the full sky map. But if you apply a mask on the sky, you have a value of 1,000 also. So this number is significantly lower than 8,000. So using simulation to quantify these, what they do is that they basically simulate lots of isotropic universe and calculate the probability to get such a low value in the isotropic universe. You see it's pretty low. And therefore they argue that most of the large angular correlations in the reconstructed sky map are inside the part of the sky that is contaminated by the galaxy. But what we think the reason to get such a low probability value is because people use a direct pixel estimator of angular correlation function on the car stack, which will be true to be suboptimal. And also they use a posteriori choice of the S1 half statistic. So it's basically a combination. This low probability value is a result of the combination of using both the suboptimal estimator and the a posteriori choice of the statistic. On one hand, we will see these separately. If you use a slightly different estimator, this is the quadratic maximum likelihood estimate, QML quadratic maximum likelihood estimate. Then no matter whether you apply the mask or not, you will always get very consistent C of theta correlation function. And none of them is flat above 60 degrees. So this is no mask, you have this black real line here, and taking 75 mask or 85 mask, you get very consistent result. And this estimator actually effectively performs the reconstruction for the ALMs, but using the assumption of secure isotropy to downweight the ambiguity mode that are poorly constrained by the sky cloud. This is a really technical description. So I illustrate how one can do this kind of thing. Actually do a basic map making equations where you can just from the structure outside the gradient plane recover.
The ILC map, that's like an extrapolated map for the, so like maybe you can clarify this. That's the map that's extrapolated to be below the mask or something like that. It's not.
Well, what do you mean by?
It's not extrapolated, it's just a linear combination.
Yeah. That's what you mean.
Just a linear combination.
I see. So the mask.
And we
so
do not use for analysis.
Yes. Right. And so the mask ILC map is the same. Would be the same as just the normal science map. No. So why is this not done? Aren't people doing this with just this instead of using a mask ILC map? Why aren't they just using the normal science map?
Yeah, they can use. Yeah, they can use. But here, I mean, because we want to compare the car sky map with the full sky map, so we use ILC basically to see whether because ILC most of the galactic contamination is cut off. It's already removed. There are some residual ones, but not very strong.
But I understand that the noise properties are really complicated for the ALC. I mean,
But for
what
noise,
you're saying, don't use for science, right?
no, but for the lowest multiples, the noise is not very strong.
So no one's claiming that there's cosmological uncertainty. There's something cosmological they're not almost here. It's just people are just trying to understand the effect of mass, right?
Well, we should probably look it up. But the honestly, it's not. We stamp that on, but it's not.
But I had a question. You showed the just the previous figure in the very first time you showed the correlation point. There was a prediction from the normal cosmology, and one could see that it was sort of like what you got from the data was kind of outside. I understand that the band which is shown there is the cosmic variance limit probably, or is that wrong? I mean, what is the band?
So actually, this one isn't very accurate because this is so-called 1 sigma band from both the cosmic variance, basically the cosmic variance. But the problem is that actually different CITA angle actually highly correlated. So there's actually which means that these points the error bar is highly correlated with the other points. So this is actually not a very misleading plot.
Yeah, no, I mean, but there's two things that you could take away from this plot. There's one thing, it doesn't lie in this blue band. And second thing, it doesn't show this high angle correlation. I mean, there's no, right? I mean, that's sort of the indication. So
yes.
I was wondering, the plot you showed with your method, can you show a similar prediction from the normal lambda to the end? Maybe it's too technical. Let's go on.
That would be the same. So
it's exactly the same. Yeah.
And the anti-correlation has one thing doesn't correlate.
Okay. So this is ILC map. As we see, that if we smooth it to L max to 15, it's enough to compute the correlation function. So smooth it to L max to 15. And here are the two masks, like 75 and 85. So multiply the mask on the map, you get the Cascade map. And using a very simple, very basic mathematical equation, you can successfully recover the structure along the galactic plane. And here, from this map, if you calculate the C of theta angular correlation function for the full sky map or for the Cascade map, but after you do the reconstruction, they all see. You see they are all very well consistent with each other, and none of them is flat on 60 degrees and above. Okay, so WI 7 years paper, Burnett et al. 2010, they say that this paper, FW et al. That paper also reconstructed the lowest multiple across a program sky cloud region in a manner that was numerically stable without assumption of single isotope. And so this is so here I show that one can actually very well recover the region of the galactic plane. And the reason that that estimator is suboptimal shown basically in Anisotropy paper. So this pseudo CL estimator compared with projected maximum likelihood estimator. This one is mathematically equal to that direct picture estimator, except that this one assumes the isotope, the structural isotope, but we can treat them mathematically equivalent. So compared with this estimator, you see that by input a value of quadruple value and octuple value, and doing the subsequent estimation by using these two estimators, you find that this estimator has larger variance than the other side. So this one doesn't converge as well as this projected maximum likelihood estimator. So this one is optimal than this the other. Okay. Here we see that there are actually different estimators. But the real reason to get a very strong significant result is because people use a
before doing that, can you write your estimator or can you show us the estimator?
which one?
The maximum likelihood is that what is the maximum likelihood?
Yeah, so that's basically you work in L space rather than the real space. Because in real space, after you apply a snapshot, it's not completely orthogonal. You know, your function doesn't really orthogonal.
So you measure the ALM with the of the mask map.
I measure the ALM of the map. Yeah.
And then.
So basically you measure you form another estimator of in the L space basically, and using that to estimate the ALM. I can show you what I did before. So that also listed in Tim Mar's paper and I can show you how to do it. Okay. So the reason that is because there is an A posterior statistic going on. And what is A posterior statistic? Here, I mean, this plot, these kind of SH initial basically characterize this problem of A posterior statistic. So this is the map, and you can see that on this direction there could be a ledger of SSH on this map. And actually, this is the most of the question, the question that most of the CMB analysts ask. So what is the oddity can I find in the data given the number CDM model? So what is the oddity I can find within the map? But however, I think the most central question is to ask in a basic way. So given this is the data, because this is only CMB fluctuation we can observe, so what is the probability of the number CDM model to be asked in the object? And I can illustrate this by by doing this experiment, the removal of ISW signal. As you know that the contribution to the temperature fluctuations from the time varying potential is called the ISW signal. So delta T over T is temperature anisotropy is from the integral of the Lyell-Side integral of the time varying potential from the last interface to the third time. So on the left-hand side, these three plots are the potential, basically, reconstructing potential from the two mass density survey. And therefore, by plugging into these phi potential into this equation, we can figure out the contribution contribution from this kind of time-varying density field to the ISW signal. So therefore, these three slides are the three redshift slides of the contribution of this delta T ISW. And then you can add in all of these maps together to get the total contribution of the ISW. And these ISW signal are actually not primordial signal, not from the last interface. So one can remove these from the map. And after you remove these, you get a local ISW corrected map, and then you compute the C of theta function as a function of theta. So no matter you see that no matter whether you have a mask or not, they all show appropriate strengths above 60 degrees, and none of them are as flat as 0. And also you can compute the S1/2 number as we see before. It is an integral of C of theta above 60 degrees. And you see that for the full scan, you get 10,000 microkelvin to the fourth. And after you apply, even though you apply the mask here, you get 5,000 or 6,000 these values. So none of them is as low as 1,000. So it means that they're all very consistent with concordant LMC level at a few percent level. So it means that if you originally get a map with already ISW corrected, then you plot the C of theta function, then you see appropriate strength on different scales. Then you wouldn't invent such a statistic to characterize the significance. So unless you really want to argue that there is a physical alignment of the local structure with the potential fluctuations at the last interface. So one is a very local structure. The other is something happens at redshift 11,000. These two things conspire to remove the large scale correlation outside the galactic mass, which is such a theory is really implausible. So otherwise, you have to admit that the estimator you use is a kind of an A posterior estimator. Sorry, the statistic you use is A posterior statistic. So here I basically, first part of the talk, I want to argue that there is really the argument for the method of large angular correlation isn't really justified correctly if you consider both the estimator and also the a posteriori properties of the statistic. So Charles Burnett et al. And as well this is paper. So but since the full sky contains a superior sample of the universe and the car sky estimate suffer from a loss information, car sky estimate must be considered suboptimal. It now appears that Spurlow et al. 2003, Kobe et al. These two papers, low p-value result from both the a posteriori determination of x1 half and the chance of alignment of the galactic plane with the CMB signal. So it's a kind of a posteriori definition of this statistic, and also there's a chance of alignment between these two, and they give the result eventually. And but yet there's no large scale cosmological significance to the orientation of the sky path or the orientation of the local distribution of matter with respect to us. Thus, the result from Spurlow et al. And Kobe et al. Must be a coincidence. So there's this problem. So in my second part, so in my first part, we talked about angular correlation functions, and we use WMAP data to basically testing these correlation functions and see whether they are consistent with lambda CM. And in my second part, I want to discuss the very recent progress on the direction, how to test the direction-dependent power spectrum with Planck, and why this is interesting to the theories and also to the observers. As we see that WMAP, these are the very early papers, not very early, actually 8 years ago. So 2003, people find the alignment of the quadruple and octuple beyond basically on single directions. And later on, these theories, Altman, Sharrow, and Carroll, and Weiss, they propose a so-called A, C, and W model, which is a direction-dependent primordial power spectrum, to try to explain the alignment of the quadruple and octuple. And this is the primordial direction-independent power spectrum. It's still invariant power spectrum, G of K. And they multiply it by a modulation function as you see G of K as a function of wave number. And also there's a modulation function as a direction-dependent factor. So this is a quadruple modulation here. And we see that this n actually is a direction on the sky. So it's a two-dimensional, two parameters basically in terms of the angle. This is their, and they use basically a simple model of the inflation trying to produce this primordial power spectrum. Basically, they assume there could be some kind of vector fields not completely decaying out during inflation, and this vector field can produce some different direction on the sky. And later on, these Dworkin, Harris, and Wen-Fu, they also have another their model of basically have a large-scale modulation of this potential field, and through the Anisotropy effect, this one will project you a temperature anisotropy on the sky. So by modulating these potential fields, one can get also a kind of fluctuation, this temperature fluctuation anisotropy, and produce you some alignment. And this is the result of quadruple and octuple. The Norway group, this guy, Gutenberg, probably also you know them, but I didn't make it before, but he published a lot of paper on this. So he tried to use this ACW model, and try to see whether we can see it already from the WMAP data. And by assuming, to go back, by assuming a constant modulation, G of K, so G of K is a constant, just one number, we can call it G star. By quantifying this as they think that it's assume this is a constant, basically. So then therefore they have a 3-parameter model. So G is a 1 parameter, and N is another 2 parameter. So direction is another 2 parameter in terms of the angle. So they fit these models on the sky. And by applying the W band, V band, and Q band data, and using the K-75 mass, they find some amplitude of the G star and also this direction on the sky. So if you just see the G star values, you see that there are some value of detection. But however, later on that Duncan, Hansen, and Lewis, their company, they argue that this kind of preferred direction on the sky is due to the asymmetric beam on the sky. So there's some argument and debate on this. But however, it still might be systematic, as we say mentioned about Duncan, Hansen's and Lewis paper. So the real question we want to ask is this power spectrum really direction dependent? And if it is, then this is anisotropy really active symmetry. It could be that, as we see in the previous model, they assume a preferred direction on the sky. But if the anisotropy may not be completely direction dependent. May not be completely active symmetry. It could be the pattern could be more complicated. And therefore, if it's active symmetry, there is some anisotropy there. Then we need to point out whether it is active symmetry. Then we need to approach the preferred axis. And at the same time, to answer all of these questions, we also need to take into account the more and more precise data of polarization possibly be taken, measured by Planck, and also the future experiment, as we just heard those kind of ground-based experiments. So as we know that you see the Planck, this is the Planck scientific program, we see that Planck has low frequency, 3 channels, and more important cosmology. For cosmology, it's more interesting to see these kind of 6 high frequency channels. And it does improve the resolution much better than WMAP and the previous code. And it does actually improve also the measurements of both the temperature and also the polarization. These are the comparison between the WMAP and Planck measurement of the angular polarization. This angular power spectrum CLs, and also this close power spectrum CLT. So then we need to, because we know basically from the scientific program of Planck, basically we know what could be the frequency, what could be the noise per pixel, and for different frequency channels. So we can try to forecast whether Planck could be able to see such kind of anisotropy on the sky. If the sky is completely circular-tropic, then these ALMs are Gaussian variables. So these ALMs could be decomposed from your temperature fluctuation on the sky by doing this integral. And if this is Gaussian variables, then this average is equal to basically coordinate matrix, which proved to be diagonal. So, but if the temperature fluctuations have some anisotropy components, then these ones are not completely Gaussian variable, and this average has some off-diagonal term here. For instance, we see these active symmetric assumptions. So generalizing these active symmetric assumptions. So if we have a power spectrum P of K, which is not only related to the scale invariant power spectrum, but also there's some direction dependent terms. And we see in the previous paper, people assume a direction dependent case. So basically, they assume a G star, which is the strength of strength of these modulations on the sky, and also they assume a direction n, which is a 2-parameter direction. But one can actually generalize these active symmetric case to include more possible more complicated patterns on the sky. So this P of K becomes this modulation power. You can expand it in general with some YLM here, and therefore this ALM, as we see, it is basically doing these projections of in the K space, and we know that this primordial power spectrum is basically follow these chi-zero average of the beats. But here now we have a modulation. not only is the scale invariant power spectrum, but also there is some second term. So if there is some modulation for the primordial power spectrum, then when we do this ALM average, there is not only the isotropic diagonal part, but also some anisotropic off-diagonal term. So the task is going to measure this kind of off-diagonal part of the polarization. So the isotropic part, of course, is linked to this power spectrum, both the autocorrelation and also the cross-correlation. And the second term, this is the off-diagonal term. Of course, this will link to this modulation part. This one will directly proportional to this GLMs. Yes, so these link to these GLMs, and also the other integral, this some geometric factors, and also link to this correlation between different modes. And to do the forecast later, we need to basically remind for the noise level for plant and for both the temperature and your power spectrum, and also this kind of CLE, which is the E-mode power spectrum, because we want to see whether plant will be able to improve all of this. Okay, so by calculating the Fisher matrix, we therefore know the error for the anisotropic parameter GLM. So this is a Fisher matrix, and we can see that this is the result. So we can see that if we use the plant first year temperature data, we can get this red line here. And if we use the second year, which is basically include the extended machine, then we get this blue line here. So that does improve. If we include, usually it does improve a lot. And this x-axis is the number of modes we include, is Lmax values. If this is the temperature map, and if we include polarization right here, and if we include polarization, what we can get? So the first year, if we just using the E mode, then we get this green line here. But if we incorporate the secondary mode, then we also improve a lot. And because for the E mode polarization, the noise just blow up very easily. So by including, if we including too much mode on Lmax above 1,000, then it didn't improve a lot because the noise just dominates on higher L. So this is for the, but it does kind of provide you a complementary check for this anisotropy on the spec. And of course, the most the powerful constraint comes from the combination of both the temperature and E mode map. And these are the ground line is actually you combine all of these things together. So yeah, so this is the error for the plant to detect such kind of active. Sorry, to detect such kind of modulation on the spec for the primordial power spectrum.
But you showed that you use the very general expansion of the possible anisotropy, the power spectrum material, just the quadruple part again, right?
Yeah.
So is there anything you can learn about the higher?
Yeah. So you can do higher, but even for the quadruple, you generalize.
So small. So in other words, you could have skipped the full expansion. You can just take the what was it, ACW.
No. Even for L equals to 2, it actually has is more general case than ACW. So L equals to, you have 5 parameters, right? But ACW will have 3 parameters. So ACW has G star,
Okay, I mean it's a full quadruple. Okay.
Yeah, it's a full quadruple. And this is the error basically we forecast for time. And the most important thing is that if we get a map, then how we can basically estimate the amplitude basically of all of these coefficients, G2Ms. So we can actually test a pipeline for this estimator. This estimator is basically a quadratic estimator for after you obtain a map, then how you can compute basically the estimated GLM maps. To basically to test this kind of thing, we can basically simulate a map and test these pipelines. And this is a simulation of the map. If you, the left-hand side is isotropic map, and the right-hand side is the pure anisotropic part of the map by substituting this G2N, G20 equals 1. So this is the anisotropic part, this is the isotropic part. We add them together and to test whether these kind of estimators will pick them up. And this is the anisotropic Q map and U map, because we also want to test whether the polarization, we can also apply that polarization and see whether the polarization can provide some complementary information for this anisotropic.
So how does, did they, was in the paper of Hansen and Lewis, was there any discussion about how the lensing aspect, I mean the normal lensing, it also leads to kind of, these kind of changes in some sense, but of course they have probably very different signals. So I mean, did they comment on that or?
Yes. So I think that's a matter of scales, right?
Yeah.
I mean these might
But you can have the dipolar, those lensing here, you can have quadrupolar, you can have everything that's very small.
Yeah.
I mean that's what I'm asking.
Okay. So these, you see that, so now we apply that estimator as well, simulating that, and see whether we can pick those kind of anisotropic information out. This is estimated G2N, G20, and this is estimated G2E. So we show these two as an example. So we see that the red line here is the error estimated from the temperature of it. If we have different simulations, we see that by including more and more modes, these different simulations can always average to these kind of errors within these errors. And also as well, this for this G2 minus 2 components, if we include more modes, they also average to this they also all average to this allowed error bars by the temperature. And the same thing for the polarization and for the polarization combined with temperature as well. So these are several other things we can basically see. This is the polarization, as we say that because of polarization, the noise just grow up very quickly. So by including more and more modes, it doesn't actually help because this error, we see this error goes very fast. And it doesn't, because the noise grow up, so we can't really decrease these errors by including more and more modes. But however, it does actually provide you a check of this anisotropic. And these are the combination of both the temperature and also the evil polarization. So for a short summary, therefore the Planck temperature map should be able to constrain the amplitude of any spherical multiples of a scale invariant multiple symmetry at 0.01 level at 2 sigma. Almost independent constraint can be obtained from polarization at 0.03 level after 4 full sky surveys, providing an important precision check. So after you estimate those kind of amplitude of these 5 parameters, basically for a portable modulation of the polynomial power spectrum, then our question is, if the anisotropic parameters are reconstructed from the Planck map, and the errors are estimated, and how to know that whether this set of values indicate a preferred direction of the sky. So if it is, then it may mean that ACW model is there, but this is a thing that one need to basically confirm. For the first one, for the very simple method, you just reconstructed this GN basically on the full sky and test it by your eyeball. You just visually see if there is a preferred direction, then there is. For instance, if you have a preferred direction along the z-axis, you will get a map, something like this. But more rigorously, you can fit a preferred direction model. We know that we estimate those kind of G2Ms, like the 5-parameter model. In principle, you can fit more parameters like expanding L to higher moment. Then you can try to check that whether those kind of parameters actually indicate a preferred axis by fitting that to the ACW model. So So ACW has 3 parameters. You see whether your 3-parameter model can fit those kind of data. So this is a transfer of those preferred directions. Because your G2Ms, these 5 parameters are in the galactic coordinates, and you can transfer it basically into a frame where the G star has a maximum value, basically. So you can transfer it by rotating, doing this rotation. And these are different coefficients for these rotations. And then you can treat doing a chi-square treatment of your observed G2M values and minus your transferred G2Ms from this ACW model, which is G star and the 2M. And these, you see that these you can get some, here is some simple simulation, and you can get basically a constraint of this angle x and y by using the temperature and E-mode here. And as well as we say that we simulated a map with G2Ms equals to 0.1, and you see that by using the temperature only and also by using the E-mode only, we can find the likelihood for the input G star. So this basically can fit quite well. So this means that our pipeline really works quite well in finding such kind of anisotropy modulation. Okay. So here is some explanation of how this works. Actually, you can transfer these G2Ms back to the coordinates, which can maximize G to 0. And if the other coefficients are small compared with the error, then there is no evidence of deviating the active symmetric cost value. So in general, one can do this basically by using this kind of likelihood method. Okay. So in the second part, we talk about if the temperature fluctuations, if the CMB fluctuations has some actually preferred directions, then how we can find it, or it has more complicated anisotropy, then how we can find it. So this is an event for our example. We actually use concept to see whether both the temperature and the polarization map will provide us some important information on testing the anisotropy. So for the last part of my talk, I quickly mention on how to, basically one can actually test the early universe model with a future CMB experiment, in particular with more emphasis on using the B-mode polarization and how to test the model of the early universe as serious really interest. And as you probably know that the CMB B-mode polarization actually the polarization Q and U parameters, these two slope parameters could be decomposed because they are all function of the angle on the sky. They can decompose by using the spin basically spin tool, spherical harmonics. And these coefficients could be rearrangement. You have some plus minus. Basically, they linearly combine to form the scalar E and B field on the sky. And therefore, you have this scalar E and B field. And E-mode polarization is something like a divergence, it's a curve-free mode. And B-mode is so-called divergence-free mode. And as we see that only the B-mode can carry this basically very important information for the tensor calculation. So the reason that people using the B-mode polarization is not only it really carry over the gravitational wave information from very early universe and not mixing with density fluctuations, but also because it also suffer very least parametric degeneracy. So although the data isn't very good at the moment, but because it has these kind of generic properties, it suffers least parametric degeneracy. And this is a plot by Lewis, anti-Lewis, and anti-Chalmers. By just using the WMAP first year data result. So these error bars, you see these error bars, are the uncertainty if they substitute the parameter uncertainty, all of the parameter uncertainty of WMAP first year result into their like CAM chain or cosmological chain. And you can see that basically only on very large scales, these B-mode, tensor B-mode polarization has degeneracy with the optical depth tau. But on the other scale, actually, you see see the error bar is very small. So it doesn't actually degenerate the other parameter too strong. And this is the LR tangent to scalar ratio equal to 0.1, and this is equal to 0.10 to minus 3. So the amplitude shows very much different. But actually, they only suffer actually from the basically strongly suffer from the degeneracy with the tau parameter on the very large scale. But on the other hand, it also has some problems. The first of all is dominated by noise, as we know that from the previous people talk, or discussing this. It actually dominated by noise, and also there is some lensing confusions. And these you see is unlensed map, you see lensed map, and lensing can actually convert some of these temperature and also the B-mode polarizations into B-mode polarizations. So effectively, it will add as a noise. It will add as a noise. So when you're doing some estimation and or doing some forecast, this lensing also needs to be taken into account. So why this B-mode polarization is important? This is because it's linked to the problem to determine the very benchmark value of the tensor to scalar ratio parameter R. This is so-called blind spot. This very important value of R basically linked to both the amplitude of the annual scale of your inflation, and also it's linked to the range of the field which evolve over the inflationary period, delta phi. So if R is greater than 0.01, then it means that the field is evolving. Basically, this field is evolving over the constant scale. But of course, this is for the very simple single field slow inflation model. And now people, in this community, in the theory community, they try to do some shield symmetries, and therefore this relation may not still hold. But I mean, for the very simple single field slow inflation, this benchmark value of R basically linked to this 0.01, basically linked to this delta phi or maximum time function. And also for the single field slow inflation, the value of R related to the tilt of your tensor power spectrum, NT equals to minus R over A. This is for single field slow inflation. So if your inflation is not completely slow, then here you have some modulation factor. Normally it's modulated by 1 over CS, the non-trivial sound speed. and the tensor fluctuation on K-space projected on the two-dimensional sphere, then you can obtain this COV. And before we explain this part, let me just simply explain. This is the cosmic string from the D-brane inflation. That you have some basically it assumes that the real universe basically embedded in the high-dimensional origami where the two branes just approaching each other and collide and thermalize the cosmic band. And the leftover is this cosmic string, which people have calculated that the string, basically the power spectrum CLBB would be proportional to the square of the string tension parameter. G times mu. Mu is the string tension parameter. G is the gravitational constant. And here I put together all of the predictions from the theory and the current obtainable basically data from the ground-based experiment and the WMAP. So this single field slow inflation with tensor to scalar ratio of 0.03 as shown in this blue line here. It has large scale reionization bond, middle scale recombination bond, and it becomes lower at higher L. And for the cosmic string with G mu basically equals to 10 to the minus 7, we have this pink line here. But this pink line is on this higher kind of higher moment of L basically is very well under this green line, which is a lensing effect. So lensing here is a matter of the scale. So lensing here really, if you want to see any signal from cosmic string, it's becomes quite difficult. And unless you can de-lensing to some level. And For the data, for the very large scale, this is WMAP 5 years data as plotted in these black arrow bars here. And for the bicep data and for the core data, these are the two ground-based experiments. I showed them in the middle region. This bicep data, core data is on smaller scales. Yeah. So this is so because for the very large scale, as we see that these value of R basically highly degenerate with the tau. So we will not use the WMAP 5 years data in the current parameter estimation. We only use bicep and core, and we see how well we can get from these two data sets. And here is the result for the single estimate of the single field throw inflation. By using bicep only, you get a pretty well peak. Although it's sometimes zero, but the peak is pretty narrow. But this core data didn't really work very well. You see, you can't constrain this value of R. But if you combine these two, no matter whether you use conventional chi-square or use some other trick of the latitude, so-called hyperparameter, these two have some difference. But in this content, it doesn't differ a lot. So let's see that by combining these two, no matter what kind of combining method you use, they also very consistent with all these bicep. So bicep is the current dominant basically data set to determine this value of R. And if you use if you constrain the cost constraint tension from this given data set, so you see that for the bicep data, it can be a pretty well upper bound on the G mu value, less than 10 to the minus 6. But if you use core data, you get a very strong peak here. We seem to be a detection of the G mu, but actually some part of the core data, especially for the L less than 500, has some actually systematic errors. If you remove this part of the data by using just the plot with L above 500, you get a brown curve here. It's basically very well consistent with the upper bound given by the bicep, 10 to the minus 6. If you combine these two, of course your constraining power improves. But basically the current upper bound from just the B-mode polarization would only give you a value of G mu less than basically 10 to the minus 6, or you can say 5, 10 to the minus 7. So yeah, this is the current constraint. But how much we can improve from the future experiment? This is the signal to noise, R over delta R, to fix your NT for different future experiments. For this plant, we show it in the black line here. And for this CMB pole, which is a pretty futuristic experiment, we show it in this very deep purple line here. And in between, actually, we have this spider, which is a boom ball experiment, and also the polar bear type. So these two ground-based experiments, plus this boom ball experiment, does improve plant in some at some certain levels. But the interesting thing is to notate this kind of detection limit, which is around 10 to the minus 3. So if your tensor mode is kind of even lower than these values, then I think it's possibly quite difficult to see any of these signals. So this is we can remind this value as some detection limit. And this is a delta t, delta nt, which is the slope of the tensor cross spectrum. And delta nt equals to r minus a. This is basically a line to see whether the experiment can see the consistent relation for the single field throw inflation. Of course, if you have a non-trivial sound speed, then your tilt of the tensor cross spectrum could be quite large. But this is for the single field throw inflation, simply small. So if we want to see any of the tilt, then we have to find the NT basically less than this delta NT. So we need to restrain us only to this angle, to this part of the plot. So we see that only the CMB pole, this purple, the very deep purple line, with R, this R value, this x-axis is R value. So with only R greater than 0.01, that we can see this tilt of the spectrum, which means that only the CMB pole with R greater than 0.1, we can see this tilt, unless you have unless the real universe, it is not single field throw inflation, if the tilt becomes bigger, then this line can be moved on the other side. But for the simplest model, you see that it's quite difficult to detect this kind of slope of the tensor crossway. And what about for the cosmic strain? This is the G mu value. This is mu over dot mu, signal to noise ratio. So we see that for Planck, it can basically constrain this G mu value for less than 10 to the minus 7. And this ground-based experiment, like this polar bear quiet and basically polar bear quiet, can improve Planck quite a lot. This is because this kind of experiment focuses on smaller scales. But Planck, the noise will blow it out on small scales. That's why this ground-based experiment is better for finding those kind of cosmic strains. But I think the interesting thing is to see the detection limit. Even for CMB 4, you see if your G mu value is less than 10 to the minus 8, then it's really, really difficult to see. So 10 to the minus 8 is some kind of detection limit. Conclusion. So in this part, we basically describe that at the moment, you see the bicep data can provide you very strong constraint on the value of R and also give you an upper bound on the G mu value, which is nearly comparable to the other combined data sets from WMAP and also from the other experiments. So, which means that the power of determining these kind of model of the early universe from the B-mode polarization is really comparatively very good. But the only thing is that at the moment the data is very good, but its intrinsic power is really good. It has a perspective to really give you a very important information of these models. And for the future experiment, Planck and the very promising ongoing ground-based experiment can also improve you a lot. So at the same time, we also need to kind of be careful for the detection limits of the things. Okay. My conclusion for three-part of my talk, basically, we test the anisotropy of the CMB from different perspectives. The first one, there's no real lack of large-angle correlation function. On the CMB side, previous use as not have statistics is equal to the statistic. And the second part, we try to test this anisotropy, test this modulation of the primordial power spectrum for the Planck satellite. So the WMAP B and W band data show the evidence of the direction-dependent power spectrum. We see these in the other people's work, and it can be strongly constrained by the temperature and polarization map all the time. This is what we discussed in the second part. Finally, I say that the B-mode polarization data can provide an interesting constraint on the early universe model, and the detection limit for R is about 10 to the minus 3, maybe a little bit lower, but it can't really test R on 10 to the minus 5. And for G mu, which is the strength of the string tension of the cosmic string, which is the limit for this 10 to the minus 8. So I think these are my summary of the talk, and I think these and many of the topics we are discussing today detect finding lack of large-angle correlations, or finding anisotropy on the CMB side, and finding the early users kind of detect whether we can detect the CMB B-mode polarization and see whether we can see the B-mode polarization, see the early users models. I mean, these topics that we are discussing today seem to be interesting and may confront astronomers and cosmologists in the coming days. Thank you very much.
Any questions? We'll just adjourn the